technology is influencing and improving our way of life, and metaphysics of artificial intelligence is evolving, projecting a new paradigm in the design and development of ASIC, cognitive system on chip, CPU for neural morphological systems. The objective of this framework is to illustrate an actual engineering prototype model of a cognitive artificial intelligence neuromorphic ASIC architecture integrated at a system level by a 5-stage pipeline architecture, the arithmetic logic unit, the finite state machine, and the first in, first out VHDL represented in orthogonal architectures in mathematical algorithms. The instruction fetch stage is composed of 3 components: the instruction memory, the memory counter, and the instruction address adder. The instruction fetch is responsible for reading the instruction memory and sending the current instruction to the next stage within the pipeline. The instruction memory also takes inputs from the outside world that allow the loading of instruction memory for later execution. The decode stage is the stage of the pipeline where the fetch is decoded and values are fetched from the register bank. It is responsible for mapping the different sections of the instruction into their proper and correct representations. The opcode and function codes are sent to the control unit, and the outputs of these corresponding components are then clocked and stored in the next stage. The execute stage is tasked for taking the data and actually performing the specified operation on it. The execute stage consists of the arithmetic logic unit, a determined branch unit, and the forwarding unit. The execute stage connects these different segments together so that the arithmetic logic unit will process the data, given inputs chosen by the forwarding unit, and it will notify the decode stage if a branch is taken. The memory stage takes the output of the arithmetic logic unit and puts it into the proper memory location if the instruction is a store. The memory stage contains the data memory object. It connects the data memory to register bank for the write-back stage to read and also to forward on information about the current write-back register. The write-back stage writes the calculated value back to the proper register. It has input control lines that tell it whether this instruction writes back or not, and whether it writes back the arithmetic logic unit output or the data memory output. The arithmetic logic unit is capable of calculating the results of a wide variety of basic arithmetic and logical computations. The arithmetic logic unit takes as input the data to be operated on-call operands, and a code from the control unit indicating which operation to perform. The output is the result of the computation. So the ALU, the arithmetic logic unit, will perform the following operations. The arithmetic operations, that is, addition, subtraction, increment, decrement, transfer. Logic operations such as AND, NOT, OR, NAND, NOR, exclusive OR, and also exclusive NOR. The objective is to show the implementation of a 32-bit arithmetic logic unit using the behavioral model style to describe how the operation of the arithmetic logic unit is being processed. It is accomplished by using the hardware description language, the VHDL. The behavioral style makes use of the process statement. The process statement, which is the main construct in behavioral model, allows using sequential statements to describe the behavior of the system over time. So a process is declared within an architecture as it is illustrated in this video and is a concurrent statement. The statement inside a process are executed sequentially. So the process reads and writes signals and values of the interface, which is input and output ports, to communicate with the rest of the architecture, like other concurrent statements. As I have illustrated and shown in this video of the arithmetic logic unit, I have used several constructs to model the VHDL process statement. Also, I have used the when statement. In the case statement, it executes many sequences of statements based on the value of a single expression. Also, the case statement evaluates the expression in comparison of the value of each of the choices, while the when clause statement corresponds to the matching choice, which will make the statement to be executed. Finite state machine, FSM, is a paradigm mathematical model whose output is dependent not only on the current state of the input, but also on past input and output values. The state machine generated in VHDL, as I have presented in this video, are clocked processes whose outputs are controlled by the value of a state signal. The state signal serves as an internal memory of what happened in the previous iteration. Using the state signal, the finite state machine, the case statement contains a when statement for each of the possible states, causing the program to take different paths for every state. The when statement can also contain code which should be executed while in that particular state. The state will then typically change when a predefined condition is met. The control logic drives the FIFO flag. FIFO empty, that is flags no data is present inside the FIFO RAM. In the FIFO full, no data can be written to the FIFO memory. And FIFO almost empty / full is also supported. So the FIFO almost empty flags is when the FIFO is used in order to buffer input data stream of a device where the input and output data throughput is the same, but the timing is different, such as in input as burst data, output as continuous data. The FIFO is used to buffer the minimum number of bursts data in order to guarantee continuous reading from the FIFO without interruption. So in this case, the FIFO read control logic block checks for almost empty flags going high and set FIFO read control signals to read continuously from FIFO. In the dual port RAM model segment of the FIFO, it writes counter to address the right side of the RAM. It reads the counter to address the right side of the RAM, and the control logic aiming to update the right counter at each write data into RAM, and the read counter every time a data is read or is read from RAM. The FIFO VHDL model has several settings and are configured to adjust the width and depth of the FIFO. The data width variables adjusts the size of the data in and data out buses so that one can write different sizes of bytes if needed, and the FIFO depth variable adjusts how big the internal memory of the FIFO is. In order to write data into the FIFO, first in, first out, first push the data onto the data in bus and then strobe the write enable input high for 1 clock cycle. It will write whatever is on the data into the FIFO's internal memory. Writing in bulk, the write enable signal is left high while changing the data on the data in bus each clock cycle. When the full flag goes high, this means the FIFO's memory is full and will not accept any more writes until data is read using the read enable input. If data is written while the full flag is high, it will be ignored. In the standard FIFO first in first out, when you write the first byte into the FIFO, nothing takes place on the data out bus until the read enable signal is pushed high for at least the clock cycle. Once the byte has been written into the FIFO, the empty flag will go low. To read the next byte from the FIFO, strobe the read enable signal high for 1 clock cycle, and the next byte of data will be available to read the next clock cycle. When the last byte of data is pushed onto the data out bus, the empty flag will go high. The objective is to illustrate a demo in this video. The objective is to design and develop kinematic algorithms for the control of sensory robotic systems. The kinematics is solved in the sensor coordinate. Thus, simplification of the algorithms is done when approximations are used to solve the inverse kinematics. The kinematic method is based on the resolved motion rate control, in which the required velocity of the end effector is related to the joint variables. 6 joints are required in order to position and orient the end effector in space. The kinematic robotic is characterized by the use of algorithms of reading points of 3D space, floating interpolation by a polynomial of the 5th order, iterative process of solving inverse kinematics tasks, dynamic feed-forward torque of each motor, and calculation of position control algorithm with a control loop. The sensor is able to produce 3 components of the required linear velocity of the TCP in 3 orthogonal axes, and 3 components of the required rotational rates, such as angular velocity about this axis. These technologies are used by industrial robotics for equilibrium, balancing, as well as orientation purposes. This frame of work presents the basic fundamentals from a system architecture. Some of the important technologies required to build a cognitive, thinking, artificial intelligence robotic system. In previous videos, I have illustrated several engineering prototypes representing actual architectural models, including telemetry system, inertial measurement system with integrated gyroscope, accelerometer, and magnetometer. These technologies are used by industrial robotics for equilibrium, balancing, as well as orientation purposes. The core of the robotic system includes the neuromorphic CPU in conjunction with the support of complex mathematical algorithms, software Kalman quaternion filters, servo motor control algorithms. There are other programs embedded in this robotic application within the realm of artificial intelligence paradigm, that is machine learning, cognitive mathematical representations, and convolutional neural network software models. Smart glove and bionic hand illustrating software algorithms, firmware integration, and artificial intelligence. Bionic hand artificial intelligence. Electrode sensors are placed on 2 nerves, that is the ulnar and median nerves, located in the human arm. These nerves normally would allow for certain sensations in the hand. The idea is to electrically stimulate those nerves, thus transmitting the signal to the smart glove and the bionic hand fingers to enable it for dexterity. The bionic hand receives information from the brain via the ulnar and median nerve, thus providing sense of feel, touch sensitive, essentially creating a loop to let the bionic robotic hand to communicate with the brain. Motor software. Here is an illustration of the software models which activate the motor movement. The software is created with C++ and Python, integrating solutions for pulse width modulations by controlling several analog ports located on the main computer digital platform. Wi-Fi communications protocol. Data is sent over Wi-Fi to any IoT device, including a PC computer and/or an Android device. It also communicates with the bionic robotic hand in order to control neural movement of all bend sensors and joints. Neural engineering technology. Artificial intelligence refers to a broad category of computing. System is able to learn directly from data. It is made possible by the augment of data analytics and applied by the introduction of machine learning processes together with deep learning methodologies. Deep learning applies the neural network. It is a subset of machine learning, integrating neural network techniques that enable systems to learn from large amounts of data